So a slope field is a representation of the general solutions of a differential equation. Which is actually kind of cool because, I'll preach at you a little bit while you're writing it. The general solution is an infinite number of answers. So you're able to draw a picture, a representation of an infinite number of answers, which is actually pretty neat. I won't conceal from you, I don't have a lot of patience with drawing these because it can be a little tedious sometimes, but I think the result is actually very cool. I think slope fields are a very cool thing. You're representing an infinite number of answers, which is just cool that you can do that. They are a little tedious to draw sometimes, those things. If only x is in your differential equation, then all of your columns will be the same, which is nice because you can knock out whole columns at once and it's not as tedious. If you only have y in your differential equation, then all of your rows are the same, it's like horizontally, and you can knock out whole rows at the same time and it's not quite as tedious. When you have both x and y, you kind of have to chug along point by point and it can get to be a lot. But oftentimes there's symmetry, so, you just kind of take what you get. So for each of these, and we're going to do all these things so we can make connections between all the stuff. We're going to draw the slope field, describe what the solutions look like, solve the general solution, solve for the particular solution. I'm going to give you an initial condition, and then we're going to draw that particular answer in the slope field. All right, so looking at this one, what do you notice about it? There's only x, so we're going to knock out whole columns at once. Oh, also, I need to read the fine print for you. If you are a very type A, it needs to be perfect all the time person, you're going to have to take a few deep breaths because these aren't going to be perfect. They're going to be good enough. Do you understand what I'm saying? It's just going to be good enough. So you're going to have to accept that. All right. So let's knock out this whole first column. For each one of these points, and it looks like you're playing that dot game. Do you know the dot game where you connect them and put your initials in? Anyway, that's not what we're doing. Don't do that. For all of these points, what is the x value of each of those points? -2 for all of them. So you can knock out the whole column at once. If you plug -2 in for x, what do you get? 3. Do you see how it's 1 plus 2? It'll be 3. For each of these, you want to do a slope of 3. That's up 3 over 1. That's pretty steep. So I'm going to draw something like that. It's good enough. And you kind of have to trust the process with these. It doesn't look like a whole lot until you get the entire thing done. You're going to have to just trust the process a bit. Okay. Next column. What is the x value for every single one of those points? -1. If you plug in -1 for x, 2. Now, it just needs to make sense in relation to the other one. If this is 3, 2 needs to be less steep, not quite as steep. Is it perfect? No, it's just these ones need to be a little bit less steep than those ones. Which mine, I don't like mine. I'm going to fix them. I know I just said it doesn't need to be perfect, but I kind of made them the same amount of steepness. So I'm going to, there we go. That's a little bit better. I want to be able to see that it's different. All right, in the middle, what is the x value for every single one of these? 0. If you plug in 0 for x, you'll get 1. 1's a little bit easier. That's kind of perfectly diagonal. How about this whole column? X is... Oh, you guys are jumping straight to the answer. X is 1. 1 minus 1 is 0. 0 is also pretty easy to do because 0 is just going to be horizontal. That's the correct reaction to these. This is so weird. It's cool once you can see the whole thing though. All right, and then for this, x is 2. So 1 minus 2 is -1. Now, these are all +1. You need to make your -1 match, but just be going the other way. So now what I think is actually really cool about this is that is a representation of an infinite number of graphs. We just want to describe them. If I were to draw in a graph following along with those slopes, what would it look like? A quadratic that has been good. It is a reflected quadratic. But here's what's cool, and this is the part that you got to get on board with. It's neat. It's cool, guys. You can disagree, but this is really cool. It's an infinite number of parabolas. It's this parabola and this one and this one and this one and this one and the one that goes off the paper and down the hall. You just drew an infinite number of graphs. Isn't that kind of cool? It is. It's cool. All right. Now we're going to solve for the general solution. So you're going to multiply over the dx. When the whole thing goes away, I like to put a 1 there. I feel like when it's gone, it kind of throws everybody off. So if I put a 1 as a placeholder, that helps a little bit. Then we're going to do our antiderivative. So antiderivative of just 1 dy. Just y, which is nice because the goal is to solve for y, so it kind of already is. And then antiderivative on this side. For just 1, just be x minus 1/2 x squared plus c. Do you see how they would be reflected parabolas? There's a squared and that term is negative, so it's upside down. So you're making sure those match. Again, what I want you to do here is make connections, right? Now we're going to solve for the initial condition, y of 0 equals 1. If you plug in 0 for all these x's, they're going to just be gone. And so c equals 1. Now, normally you would have to go back a step. I'm bringing that up because in all these other ones, you're going to have to go back a step. The reason you don't have to do that here is because we already have y equals, but normally you would have to go back a step, plug it in. But this one's just going to be y equals x minus 1/2 x squared plus 1. That's your particular solution. And then we're going to draw it in on the slope field. They ask you to do this sometimes. They'll give you the slope field and you have to draw in the particular solution. I'm not 100% sure how that's going to work this year because you guys are the first year that are doing this digitally. All your multiple choice, you're going to just click and answer A, B, C, D. They have a booklet for you to write in for the free response, but I'm not sure if they're going to have a slope field printed in it for you. I don't know how that's going to work. You guys are the first year, so you'll have to come back and tell me how it went so I can tell the people next year because I don't know how it's going to go. All right. But in years past, they give you a slope field and then you have to draw on it. So you're going to start at this point 0, 1, which would be right here. And then you kind of just flow along with the flow of the slope, swim with the current, so to speak. So this is going to go up and you shouldn't really go through any of the other ones. You kind of go around them. The only one that you should really go through is the point that they give you. In this case, it was 0, 1. So it's going to like do something like this. Now, if they do ask you to draw one of these in, you have to go all the way to the edges. Go further than you think you need. For example, don't do this. If you stop here, they won't give you the point. All right, it has to go all the way to the edge. So we drew in one specific answer in the infinite number of answers that there could be. Pausing for dramatic effect or if there are questions or if you want me to go on. But the point here is to make some connections, which I think that does. It pulls a lot of things together there. All right, so let's try the next one. What do you notice about this one? It's only y. So you're going to knock out whole rows at once. I'm going to speed it up this time because it seemed like you guys kind of had this part. What is y for every single one of these points? 2. If you plug in 2 for y, 2 over 2 is 1. So something like that. For the next row, y is 1. So that would be 1/2. So if this is 1, 1/2 needs to be less steep. How about for the next row? 0. Good. So for all along the x-axis there, 0. And then these are going to be the same as what you had up here, except negative. Do you see what I'm saying? Like there's a lot of symmetry in math. So you're going to take this will be -1/2. And then these ones will be -1. Now, the one we just did above were quadratics. What are these ones going to be? If you drew in a graph following along with the slopes, exponential. Good job. With a horizontal asymptote here at 0. Good. So exponential horizontal asymptote at 0. So it could be up here, or it could be reflected and be down here. Again, it's a representation of an infinite number of graphs, an infinite number of them. So now let's go back and solve it. How would you move over the y? Would you multiply or divide? You'd have to divide. So it's going to be 1 over y dy. You have to divide that y to the other side. Equals, now this 2 is still here, but where is it? Then on the denominators. So we have 1/2, and then we'll multiply over the dx. And then we're going to do antiderivative. So what's your antiderivative for 1 over y? Yep, ln y. You got it. Equals 1/2 x plus c. And then how would you get y by itself? How do you undo ln? So we always say we e both sides. The official vocabulary is you are exponentiating both sides. Remember, e is a number, c is a number. So what we do is we put that out front as one big constant, and it will look like this. I left a little gap there because there's something else that needs to go there because of the absolute value. What else do you put in? Yeah. Absolute value is the distance from 0. You can go either direction. So that means there's a plus minus. So that means the graph could be up here or the graph could be down here. That's what the plus or the minus is. Now, when we do the specific one, the particular solution, we'll choose if we want plus or if we want minus. So you go back a step. Remember, I was saying we have to go back a step before you've, done any solving. We're going to plug in 2 for x and -1 for y. So if I put in -1, absolute value of -1, 1, ln of 1 is 0. Good. Well remembered. On the other side, you're plugging in 2 for x. So 1/2 of 2, 1. Oh. Yeah, okay. And so c is -1. You can't just jump to this answer and put a -1 in there. It doesn't work that way. It's going to look a little bit different. You have to start on this step that I drew the arrow on. You're going to recopy it exactly like it looks, except instead of plus c, you're going to put -1. And then you can solve it. So you're going to exponentiate both sides. It's going to be e to the power of all this stuff. Now, usually what I get asked there is, why can't you take that -1 and put it out front? I don't know if you remember from last time, because last time was like a week and a half ago. We did one where it came out to like ln of 5. E and ln cancel out, so you can just take that 5 and put it out front. We didn't get ln of something, we just got -1. So you can't do that. You're sort of just stuck with it. Just hands off, just leave it alone. And then do I want the plus or do I want the minus? It comes from this good. You want the negative. And you will see when we draw it in. Again, we're making connections here between this. You'll see when we draw it in why it's the -1. So if you start at this point, 2, -1, that's right here. And if you just flow along with the slopes, it's not super interesting. Exponential graphs aren't super interesting. They're just little swoopy-doos. Gonna do something like that.
The arrows actually be there?
Oh, no, actually, I don't even usually draw them. I don't know why I did that. Yeah, usually I don't even put arrows. I don't know why I did that. All right, that one seemed like it went better than the first one. Now, as a heads up, I'm sorry. As a heads up, the next one's going to be a little bit tougher because what do you notice about it? There's an X and a Y, so you kind of have to chug along point by point. But I will tell you, if we do this positive side over here, you can reflect it over there. So but they are a bit tedious. I will be as entertaining as possible, but I can't change that this is what the material is. All right, so I would start with maybe Y being -1. Why would I maybe go there? Yeah, if Y is -1, you're going to end up with 0. Actually, if y, I should have started with this. Sorry, my brain went somewhere else. If y is -1, and x is 0, what's going to happen at that because that's kind of a special point. That's sort of a particular thing there. Now, we don't call it undefined when it's 0 over. Does anyone remember that word? We'll play hangman if we need to. If you get 0 over 0. So yes, indeterminate means that you can't get a derivative there. So you can't have a slope. So at this point where x is 0 and y is -1, what I usually do is bold the point. That's a Miss Cole thing. If you go to another calculus class, they're not going to do that. What you're supposed to do is leave it empty. But the reason I bold it is because if I were to just leave it empty, I would think I forgot to do something. So I bold the point to remind myself, like, I did it. It just needs to be empty. You're not going to put anything there. Cool. All right. All the other points where y is -1, -1 plus 1 is 0. So these are all going to be 0 where y is -1. And then all the points where x is 0, you get a 0 denominator. Now that would be that other word that you guys said. If you have a 0 denominator, that is undefined, which is a vertical slope. Good. See, these are all going to be vertical. It's kind of like a weird cross there. So we're going to do all the ones over here, and then we're just going to reflect them to the other side is what we're going to do. So this point is 1, 2. So x is 1, y is 2. What would your slope be? 3. So maybe like that. We'll see how this goes. This point is 2, 2. So if x is 2 and y is 2, that'd be 3/2, which is 1.5. So if this is 3, I want this one to be 1.5. It needs to be less steep. Again, just in relation to each other, they need to make sense, and you kind of just have to trust the process, all right? This is 1, 1. So if you plug in 1 for x and 1 for y, what do you get? 2. This is 3 and this is 1.5. So 2 needs to be kind of like in between them a bit. I'm gonna make this a bit. But two things. I gave you the pep talk at the beginning, and I don't have much patience for I think slope fields are cool, but I don't have much patience for them. But two things. Number one, oftentimes there will be symmetry. So if you do half, you can reflect it. And if they do have you draw one, they usually only have you do about 5 points. So I'm kind of overdoing it here. I like to do that, though. I like to try and make this like a little harder, and then that'll seem easier. Anyway, we're all going to be okay. This is the point 2, 1. So x is 2, y is 1. So that'll be 2 over 2, which is 1. This one's 1.5, so almost the exact same as that one, but maybe like a little less. All right, this is 1, 0, which would also be 1. So actually, we want those to be the same. You want to make those the same. And then this is 2, 0. So if you plug in 2 for x, 0 for y, you would get 1/2. That's the least steep that we've had so far. All right, this is 1, -2. We're almost there. That'd be -1. So this away. And then I think this one will be -0.5, right? 2, -2. Yeah, that'll be -0.5. So not very steep. So what I want you to do is take those and just reflect them to the other side. So it's going to be like this.
That is so pretty. Oh my God.
I know. See, I do like these. They are very cool. I like slope fields. I don't like drawing them so much because it's tedious. But they are actually cool. What they are is neat. I like what they are, and I like what they represent, and I think they're a cool concept. I just don't like drawing them.
I don't even know what that is.
Well, let's talk about that. You can't get a derivative here. What are some reasons why a graph would be not differentiable? A cusp. What else? A hole. It will be a critical point. An asymptote. You still didn't say the one. Not a cusp, but a sharp. It's like a corner. Okay. A sharp point. If you imagine these slopes coming in here and there being a point, good job. Absolute value.
You're so small.
With the points at 0, -1. So it's an infinite number of absolute value graphs. but no matter how you draw it, the point will be there. They could be really steep and be like this. It could be really widened out. It could be reflected and upside down. It's so cool that it's an infinite number of graphs, but no matter what, the point will be at 0, -1. All right, let's go ahead and solve this. How do you move over? And we have to keep the y plus 1 together. If you want to give that a hug, you can. How do you move that over? Do you multiply or divide? You divide. So 1 over y plus 1 dy equals 1 over x dx. So antiderivative for this side is going to be ln y plus 1. Antiderivative for this side is going to be ln x, good, plus c. And then we're going to get y by itself. So to cancel out the ln, you're going to exponentiate. Oops. We put the constant out front. Yes, they will write it that way. And then what is going to cancel out with this? Yeah, the e and the ln will cancel out with that as well. So you get plus and minus c absolute value of x, which we knew it was going to be an absolute value graph. Again, the point here is to make connections. And then your last step is to subtract the 1. And so that should reinforce for you that that point is going to be at 0, -1. Remember your transformations move down 1? The plus or minus indicates that it could be facing upwards or it can be facing downwards. Again, infinite number of answers. I hope this is answering a lot of questions that you may have had last time. Usually like here's where we tie it all together. So now we're going to find the particular solution for this initial condition. So we're going to plug in -2 for x and 0 for y. You have to go back to this step right here when we first did our antiderivative. And we're going to plug in 0 for y. Ready? Here we go. 0 plus 1. 1. ln of 1 is 0. Good job. Equals. Now, if you plug in -2 for x, absolute value of -2 is just 2. So ln 2 plus c. And so what is our c value for that particular solution? Yep, good job. Whatever that is, you don't have a calculator. So, I mean, it is some kind of decimal. So if you subtract this over to the other side to get c by itself, you're just subtracting it over. So that's why it ended up being negative. So this step where I put the arrow, you're going to copy that exactly. But instead of plus c, you're going to put -ln2. You're just plugging in what that particular solution is. And then you go through and solve it again. So it's going to be similar to what we just did for the general solution. So to get rid of the ln, it's going to be e. Now I need to review something really quick for, you know what, I'll do it on a sticky note so it ends up on my recording. Because this one, instead of adding, it's subtracting. So I need to review our exponent rule. We're going to go off on a tangent really quick. Give me a single digit number. I'll just make something up. So 2 and 3 always mess with people up. Let's do 4. So when you're multiplying, you add your exponents. 2 plus 4 is 6. Do you remember this? Okay. Whenever you divide, it's going to be like a bigger number. 7. Now 7's prime. I need something that'll divide there. Thank you. So when you are dividing, no, that's what I needed. When you are dividing, you're going to subtract your exponents. So it would be, do you see what I'm saying? So do you see how this one is subtraction? That means that we're going to divide. So it's going to be absolute value of x divided by 2. Or if you wanted to just put a coefficient in front, you could put 1/2 absolute value of x. What is that as a transformation? What does the 1/2 do to your v face? It makes it like, yeah, shrink. So it's going to be wider. Okay. So when we draw it in, it should be wider. And then your last step is that you're going to subtract the 1. So when you go to draw that in, you're going to start at the point that they give you. So -2, 0, which is right here. And you're just gonna follow along with your slopes. So it's gonna look like that. You actually can in this case. Good question. I wasn't gonna bring that up unless somebody caught it. Usually you don't want to go through any of the other ones, but in this case, both sides are linear. So you will go through that slope. But I want you to make a connection between, like, we drew this in, we knew they were absolute values. We solved it, we got absolute values. We got a particular solution, and we have the point at that 0, -1. I'm gonna skip this one for time reasons because I think we've done enough of these, but I want you to try this one with your group and I'll walk around and talk to you and then we'll go over it together. So I'm gonna pause the recording. I want you to try number 5 with your group. So do it in the order we did. Draw it first, then do the description, do the general solution, do the particular solution.
The one. Oh, that's the one that goes like a. The cube root is, wait, cube root is this, because it looks like a root. Width is.
And when you guys are looking at this, what type of graph? So we've done exponential, quadratic, absolute value. What is this one? Cubic.
Divide them by 3, but 1/3 times by is
That's fine. Just draw an arrow.
Well, we're skipping that question, right?
Yes. Yeah, just for time reasons. All right, did you guys get this? Y = x cubed plus c?
Oh, you don't have to divide them by 3.
No, okay, so you want to move as little as possible to the left side because at the end you would just have to move it back to solve for y. So the less stuff you take over to the left, the less work you have to do getting rid of it at the end. Okay, and that should match. And now we're going to plug in 0 for x, 1 for y. So c would be 1. And so you end up with a cubic graph that moved up 1. So it's gonna like kind of come through here like this.